Do you remember the year 2012? The scientific establishment across the globe was celebrating its greatest triumph. They had found the so-called Higgs boson, a particle they had been searching for nearly half a century, and it was, as we were told, the final, missing piece of their grand theory, the Standard Model. A resounding success. Decades of work, titanic efforts by entire generations of scientists, all for this moment. It seemed they had closed the book. The great map of the universe, they said, was complete. Well, almost complete. Let's set gravity aside for now. But otherwise, everything was in perfect order. But what if they were wrong? What if they celebrated too soon? Because now, after years of quiet, the very same scientists at CERN, in Europe, working on their giant collider, seem to have encountered something that doesn't just add a new detail to their neat picture of the world, but threatens to shatter it entirely. And the most interesting part is how it happened. It wasn't some planned breakthrough. No. It all began with a seemingly ordinary, routine experiment. They just wanted to run another check, to refine the boundaries of a strange phenomenon. None of them expected a sensation. No one. But the data they obtained was truly shocking, going far beyond the most audacious theoretical predictions. In the course of the experiment, massive particles, with sizes and masses roughly 1,000 times greater than those traditionally associated with the quantum world, penetrated dense, solid barriers specifically designed for their complete stoppage, in a manner that was inexplicable and impossible from the perspective of classical physics. This discovery throws a direct and audacious challenge to the very boundary that physicists have drawn for decades between our familiar macroscopic world and the enigmatic, counterintuitive world of quantum mechanics. Moreover, it forces us to ask profound questions about the inviolability of the fundamental laws of energy conservation, and, most intriguingly, for the first time, it explicitly and experimentally hints at a hitherto hidden but deep connection between quantum physics and the all-pervasive force of gravity. Leading physicists worldwide, from Tokyo to California, are already calling this result one of the most significant and potentially revolutionary since the historic discovery of the Higgs boson. To fully grasp the scale of what has happened, it's worth recalling what quantum tunneling is. It is one of nature's most astonishing and paradoxical phenomena. Its essence is that the tiniest particles, such as electrons, are able to appear on the other side of a seemingly insurmountable energy barrier, despite not actually having enough energy to jump over it. It is as if they pass through a wall, defying all the rules of classical intuition. This strange, almost mystical behavior, long an integral and mathematically described part of quantum theory, has already found wide practical application and forms the basis of many modern technologies. It is what enables scanning tunneling microscopes, allowing us to see individual atoms. It underlies the functioning of semiconductor devices, which are the heart of all modern electronics. And it is even the key process that initiates nuclear fusion reactions in the scorching interiors of stars, including our sun. But the fundamental limitation of this phenomenon always seemed unshakable. Tunneling was considered the exclusive prerogative of microparticles. The theory predicted, and countless observations confirmed, that as an object's mass and size increase, the probability of it tunneling drops exponentially, plummeting to virtually zero. For an object the size of a grain of sand, let alone a human being, this probability is so negligible that it can be considered an absolute zero. Until now, the entire scientific community was firmly convinced that large, visible, and tangible objects strictly, and without exception, obey the laws of classical Newtonian physics. The CERN team took an unprecedentedly bold step to test particles whose mass was about 1,000 times greater than any for which tunneling had ever been observed. By accelerating these particles to near-light speeds in the 27-kilometer ring of the Large Hadron Collider and directing them at specially created physical barriers made of an ultra-dense crystalline alloy, the researchers expected a completely predictable result: the complete stoppage and absorption of the particles. But instead, to their utter astonishment, high-precision detectors registered clear signals of particles appearing on the other side of the impassable obstacle. Silence fell in the control room, followed by a frantic check of all systems. The first thought was a calibration error or equipment failure. But this incredible experiment was repeated hundreds of times, with different parameters and on different setups, and each time the results were relentlessly confirmed, eventually reaching a statistical significance level of 5 sigma, the gold standard in experimental physics. This standard means that the probability of the observed effect being merely a bizarre statistical fluke is less than 1 in 3.5 million. This discovery directly shatters the long-held, seemingly granite-like notion that tunneling is possible only on microscopic scales. If particles this large can exhibit behavior previously considered purely quantum, then the clear boundary between the quantum and classical worlds may be just an illusion of our perception, not a fundamental property of reality. This result forces us to fundamentally rethink several of the most sacred cows of modern physics. First, the very division between the quantum and classical worlds. The long-standing ingrained belief that the strange and paradoxical laws of quantum mechanics apply only to the subatomic realm is now seriously questioned. Perhaps the entire world, from an electron to a galaxy, operates under unified quantum laws, and it's just that at the macro level, these effects become imperceptible to us. Second, Heisenberg's uncertainty principle. This fundamental principle states that it is impossible to know both a particle's position and its momentum with absolute precision simultaneously. If even large particles can tunnel, how do these fundamental limitations scale? Does this not mean that uncertainty is a more universal property of nature than we thought? And third, the law of conservation of energy. Perhaps the most stunning and intellectually unsettling aspect was that during the tunneling process, the particles, as measurements showed, momentarily gained additional energy without any apparent external source. This temporary, albeit extremely brief energy gain calls into question the most fundamental law of nature, formulated in the 19th century and underlying all of physics and chemistry. It states that in a closed system, energy cannot be created from nothing or destroyed without a trace. Another completely unexpected surprise was that ultra-sensitive instruments detected minute but distinct fluctuations in the local gravitational field at the precise moments the particles passed through the barrier. Normally, gravity is considered a force so weak at the quantum level that its effects are impossible to register in such experiments. Yet here, subtle but statistically significant gravitational disturbances were recorded, tiny ripples in the very fabric of space-time. This fact prompted CERN to immediately initiate a collaborative program with the LIGO Gravitational Wave Observatory to jointly determine whether the phenomenon of large-scale tunneling could provide humanity's first-ever empirical hints of a theory of quantum gravity, that elusive theory of everything, destined to harmoniously unite Einstein's general theory of relativity, which describes the cosmos, with quantum mechanics, which describes the microcosm. Beyond fundamental theory, these results open up a stream of exciting, almost fantastical technological possibilities capable of changing the face of our civilization. Imagine quantum batteries, where streams of electrons, by tunneling through insulating barriers, could completely bypass the traditional limits of electrical resistance. This opens a direct path to the nearly instantaneous charging of any device, from a smartphone to an electric car, in a fraction of a second, and the creation of energy storage systems with unprecedented efficiency close to 100%. Or consider stable quantum computers. Despite their colossal potential, modern quantum computers are extremely fragile and require extreme conditions to operate. Ultra-low temperatures close to absolute zero and a deep vacuum, as the quantum states of qubits, quantum bits, are easily destroyed by the slightest environmental disturbance. If it turns out that quantum effects are preserved on larger, more stable scales, it would pave the way for powerful and reliable quantum computers that operate at room temperature, capable of solving problems inaccessible to today's most powerful supercomputers. This could also revolutionize communications. The transmission of quantum information today is limited by decoherence, the rapid loss of quantum properties upon interaction with the environment. Controlled tunneling of entire information packets could completely bypass this limitation, heralding an era of absolutely secure, unhackable, and eavesdrop-proof communication channels, and, perhaps, even long-range quantum data teleportation, enabling the instantaneous transfer of information over any distance. In the defense sector, quantum radars could emerge. Systems based on this effect could potentially detect objects completely invisible to conventional radio waves, rendering modern stealth technologies obsolete and radically altering the balance of power and military strategies. In medicine and nanotechnology, if tunneling can be controllably applied at the nanoscale, it would allow the creation of drugs encapsulated in nanocontainers capable of tunneling through cell membranes and even crossing the blood-brain barrier, the brain's protective mechanism. This would revolutionize the treatment of the most severe neurological diseases, such as Alzheimer's and brain cancer, by delivering medicine directly to the affected cells. Finally, in electronics and material science, it promises the creation of zero-resistance semiconductors that could completely eliminate energy loss during electricity transmission, leading to cooler, faster, and fantastically energy-efficient electronic devices. The new discovery also resonates with deeper, almost metaphysical questions about the fundamental structure of our universe. The experiment at CERN shows that the boundary between the quantum and classical worlds, if it exists at all, is more like a blurry fog than a sharp line. If tunneling can affect the very fabric of space-time, it could be the long-awaited experimental bridge between gravity and quantum mechanics that physicists have been searching for nearly a century. Some theoretical physicists are already proposing bold hypotheses that the mysterious dark matter and dark energy, which make up 95% of our universe's mass energy, might actually arise from large-scale quantum effects similar to the one discovered. Moreover, some subtle patterns found in the CERN data have turned out to be strikingly consistent with the predictions of string theory, a hypothetical theory that posits the existence of additional, curled up, and hidden spatial dimensions. The tunneling of massive particles through physical barriers might be the first hint that these particles are momentarily slipping into such hidden dimensions, or it could confirm the holographic principle, according to which all the information of our three-dimensional reality is a kind of projection encoded on a distant two-dimensional boundary of the universe. Of course, not everyone in the scientific community is ready to immediately rewrite the physics textbooks. Critical voices urge maximum caution, pointing out that the observed anomalies could theoretically be caused by unaccounted-for systematic measurement errors or the presence of hidden, unknown variables. It is crucial that other leading laboratories in the world, such as Fermilab in the US or KEK in Japan, attempt to replicate this highly complex experiment in the near future and independently confirm or refute its sensational results. Nevertheless, the internal consistency of the data and the extremely high statistical significance of the results obtained at CERN make them exceedingly difficult to dismiss. This discovery poses both scientific and philosophical questions. Will other laboratories be able to reproduce these astonishing results? How can we build new theoretical models that can explain tunneling with an apparent energy gain without violating the global law of conservation? Could this discovery accelerate the development of quantum technologies by decades? And the main question, Does all this not point to a deeper, more fundamental structure of reality? One that includes extra dimensions or yet undiscovered principles of matter's organization? What began as a relatively simple test of a known quantum phenomenon has unexpectedly turned into one of the most disruptive and promising discoveries in modern physics. We have witnessed large particles passing through impassable barriers, inexplicably gaining energy, and even creating gravitational effects. All things previously considered absolute physical heresy. If these results are confirmed, they could change not only our technology, but our very understanding of the universe. Like the Higgs boson in its time, this discovery could completely redefine physics, but its potential goes even further. It could finally swing open the long-awaited door to the grand unification, to the creation of a single theory of the quantum and the cosmic, the microscopic and the macroscopic worlds, providing answers to the most profound questions about the nature of existence.